with the beginning of chapter 3, where we looked at vectors for a little while. Let's quickly reiterate what vectors are, how we're going to use them, etc., etc. So, first, a vector has a length and a direction, a magnitude and a direction. What does that mean, a magnitude and a direction? What does a vector tell you? So, for example, if I said the vector is represented by 20 meters at an angle of 14 degrees southeast. 20 meters at 14 degrees southeast. What do you think of?
I think southeast. I think going down to the right.
Good.
And then, what's the other part of the formula?
It was 20 meter in length, and it was at,
So
what did I say, 12 degrees
length.
southeast or something like that?
And then whatever the degree is, that's going to be to the horizontal.
Good. Now this would be 45. Does everybody see how that's working? I'm like trying to split it.
Yeah.
This would be like a 45-degree angle right here, simply because this entire angle is 90. So that's the way I start. And if mine said, if the problem said, you know, it's at 12 degrees southeast, well then 12 degrees would have to be something smaller than that for sure. So maybe that's 12 degrees. So a vector always gives you a direction, which is the angle, and a length. So let's say the length of this was 20 meters. That's what that vector would look like. So the basics of vectors we started with. We then went to talk about how vectors could be summed together graphically. Now, what I'm going to expect of you on the test, just to give you a heads up, is to be able to sum them together where you're on a graph and you physically have a graph there. So I'll give you an example. How do I import that? There's a way to do this, come on. There it is. Dropbox.
What does it say this is math equation?
All right. So let's say that. Let me just get this off the screen, actually. Let's say I've got this object here. Can I copy and paste this? No, I can't. And I tell you that the first vector, let me zoom in on this so you can see it better. The first vector's length is given by the following. Can you see that color?
Yeah.
Okay. We'll say that's vector A. And vector B is given by this blue line here. Okay, you have a clear starting and ending point. God bless you. And the starting and ending points will purposefully end on a grid line. I'm not going to make them like end on a halfway, so you have to estimate, right? No, what does he mean by that? So you see how I put the dots there? That's what I'm getting at. So the first vector and the second vector, if you were to add them together, what approach do you take? Anybody remember? How do you add two vectors together? Yes, Sarah.
So you take the cosine of the and the degree.
But do we have any degrees here?
No.
So that's for algebraic. Wait a minute and I'll let you go for that.
Okay.
But for graphical approach, what's the graphical approach that we take? What do you do to sum together two vectors?
You make a triangle out of the two ending points, or the start point and the ending point.
Yeah, you make that triangle for the resultant. So let's go ahead and do that. So this first vector is, let's see, ready? I'm going to point. This is 1, 2, 3, 4 units up and 4 units over. So it turns out, by the way, when it's 4 up and 4 over, what's this angle automatically?
Already.
45 degrees.
45 degrees. Remember, when the horizontal and the vertical components are the same, the angle's got to be 45. That's always a rule of thumb. Now, that's not even important right now. It happened to be a side note. But up 4 and over 4. What about this one? Over 2, but then down 3. So to sum these together, pick a starting point anywhere. Let's say here. Draw the first vector. Go up 4, go over 4. Put the end point. So there's the first vector right there. Then at the end of the first vector, begin the second vector. And the second vector tells me to go over 2 and down 3. Like a slope almost, right? So go over 2 and go down 3 means it's going to end right here. So if I start the second vector right here, I'm taking this point right here. That's going right up here. Go over 2 and down 3. This is over 2 and down 3. And simply connect these two. It's a terrible line. Now, the resultant vector in this case would be connecting these two starting and ending points. So how do I find the length of that resultant vector? Right? You guys can clearly add these together, but how do I find the length of that red line or arrow or ray rather? How do I find the length of it? Don't add the two together. We don't even know the length of the yellow and blue vector. We don't need to know it to get the answer for the red one, because what we have to do is transcribe it so that it looks right at the top. But the red vector is what I'm really focused on. How would I find the length of that red vector? Come on, people. Pythagorean, good, the two of you. Pythagorean theorem, please. It should be obvious at this point in time. Look, this is a right triangle. If I think of this as the base of the triangle, think of this as the height of the triangle. It's literally a right triangle there. How many boxes over is the red vector? How many boxes to the right is it? 1, 2, 3, 4, 5, 6. And how many boxes up? 1. So this is going to be a length of 6. This is a length of 1. This is the stuff you're doing when you do this algebraically, except we did this in the beginning on a graph. So this might be, in the back of your memory, but we did it on that first day. On the first day that we did vector analysis. So I got 6 squared plus 1 squared equals r squared, where this is r again. It's going to be 36 plus 1 is 37. So it's the square root of 37 is the r value. Which will probably be like what? 6 point something?
Yeah.
Is it even 6.1?
Yeah.
6.1 if you round?
Basically, yeah.
Okay. So r is 6.1 units. Okay, r is 6.1 units. That's the length of that vector. How would I find the angle that that vector makes with the horizontal? Look at the red vector. How would I find the angle that it makes with the horizontal? I'm looking about this angle right here. That angle right there. If I want to find this angle, how could I utilize my geometry of this triangle here to figure out what this angle is? Alejandro?
Does it involve with how the other angle is at 45 degrees?
No, you don't need this angle actually. You don't need this. So he's asking about this angle here. You don't need it. If you knew something, sure, you might be able to subtract, but you don't know that information. There's another way to do it. Use the geometry in the figure. Of what? So 1 over 6. Okay, the tangent inverse of 1 over 6. Where does that come from? Well, take a look. Your goal is to figure out this angle right here. This angle has an opposite leg that is known and an adjacent leg that is known. So the tangent of theta equals 1 over 6. So theta is the tangent inverse of 1 over 6. Okay, go ahead and type in your calculator. Second tangent, 1 divided by 6. What do we get as an angle? 9.5. Can others agree with that?
Yes.
All right. So theta equals 9. That's a point. 9.5. There's a decimal there. Okay, 9.5 degrees. So if I were to give an overall answer for a problem like this, I would probably say something like the following. 6.1 units at 9.5 degrees northeast. Why do I know my answer is northeast? Why do I know that my answer is northeast? Yeah?
Obviously goes east and then north.
Yeah, exactly. To get to your final point, take a look. Look where I'm pointing. Starting here and ending over here. You have to go east and then north of east. So your answer has to have units or a label of northeast on it. Okay, so again, your goal for graphical analysis for this is to literally add the two together by using the tail end to the head, the tail end of the second one to the head of the second one, connect the beginning to the end, use the length of this by getting it from Pythagorean theorem, then get the angle there from the tangent function. If I ask you a problem like this, it's going to be given on like a graph. I'm going to say, here's a vector on this part of the graph, here's another vector, find the sum of those two vectors. It's not going to be a word problem for this one. Okay? You will have parts that could have word problems, obviously, right? Like I could say, you know, this is the graphical analysis, right? The mathematical analysis of vectors, and I'll go mathematical analysis for vectors, which is what Sierra was giving us in the beginning there, we could utilize as well. And let me show you what I mean. I could say in a word problem that a person walks 7 meters at an angle of 22 degrees northeast. So what I would do right away is this. That's my beginning of that problem. If I read that statement, that's literally what I would draw. Were you with me right now? So a person moves 7 meters at an angle of 22 degrees northeast. The person then stops. They then stop. And they move south. They move south for 10 meters. Easy enough. Do I need an angle? Why not? It's just vertical. Very good. When I say south, it means only vertical. Then the person decides to walk horizontally. Or east, I should say. East for 5 meters. And finally, the person walks northeast again at an angle of 15 degrees for 4 meters. Figure out the overall displacement. Now, if it's not drawn to scale, we're not necessarily going to know if the angle will be negative or positive or where it will actually end up. But we can use our numbers to figure this out. So let's go through this method. And I showed the other class a different way to solve vectors using a table. And it might be useful for you. So again, our resultant is going to be to figure out the resultant from here to here. Right, from beginning to end. That blue line. But it's very difficult to do this graphically. So it's almost impossible unless you have a protractor and all these other measuring tools. So let's say we can figure this out algebraically, and I'm going to show you how. What you want to think about is that each vector can move either vertically or horizontally or both. The first vector, 7 meters, that moves both horizontally and vertically. How do I know that? How do I know that the first vector moves both horizontally and vertically? It causes both of those movements.
Because its endpoint is like to the right, but also higher than where it's.
Very good. The endpoint that we're looking at is to the right and up. So it literally moves right and up. Or you could say because there's an angle involved, right? Whenever there's an angle, you know you're going to have components. So this has a horizontal component and a vertical component. How about the 10 meters? 10 meters only acts what? Vertically or horizontally? Which way? Vertically. And it's going to be negative, isn't it? How about the 5 meters? The 5 meters is only horizontal, and that's going to be positive, so it moves to the right. And then the last 4 meters, again, part of it moves to the right, and part of it moves up. So when there's angles involved, we're going to have a horizontal and a vertical part to worry about, horizontal and vertical. But when there's no angles involved, this is just a negative vertical, this is just a positive horizontal. So what I'm going to teach you now is a simple table to use, and it's an easy way to do this. Okay, so stay with me for a sec. I'm going to zoom this out a little bit to put it up here in the corner. So I'm going to start by making a table. In the table, I'm going to put always 4 columns. I'm going to put as many rows as I have vectors. So start with 4 columns. Call the first column V for the vector. The second call theta. The third call X. The fourth call Y. So by the way, you know how I thought to do this? I didn't think of it on my own. I was trying to find good videos for you guys for review, and I stumbled across somebody who taught it this way with a table, and it seemed to be a little organized, and it might help you to organize your data a little bit. So I was searching for you guys for videos. So what does that mean? It means you can do the same thing when you're struggling, right? So I didn't just come up with this idea suddenly. I saw somebody say, oh, use a table method. And I was like, that's a great idea. So that's why I'm presenting this. So I'm trying to prove to you right now that when you're home, you can advocate for yourself and search online and help yourself learn, right? If you just sit there and say, I can't do it, well then it's your loss. Okay, you need to actually push yourself in physics. You can't say, I got home and I can't do this problem, I'm done. No, that's not how you stop. You don't just give up on stuff. Okay, so advocate. Now, as many vectors as there are, how many vectors were there in this problem? Not including the blue one, not including the result vector. There were 4, right? There were 4.
Yeah.
So we have 7 meters at an angle of 22 degrees. We've got 10 meters, no angle involved. We'll explain that. We've got the third one, which was 5 meters. Again, no angle involved. And the fourth one, which was 4 meters at an angle of 15 degrees. Now, look at the first vector. 7 meters moves to the right and it moves up. Everybody agree with me? It moves to the right and it moves up. So both x and y are positive for that one. It moves to the right, which is positive x, and it moves up, which is positive y. How about the second vector, 10 meters? Does that move left to right at all? So you can simply just put a 0 here for x. It doesn't move in the x direction. Which way does it move though, Theo?
The y direction.
And which way does it move?
Negative.
Good. So here I can put a negative. And its value is just going to be negative 10. I can plug that in right away because it's all in the y direction. When there's no angle involved, the 10 meters of length, since it's going down, means you're going to have negative 10 in the y direction from that vector. How about the 5 meter vector? Does that move left to right or up and down? Left to right. Which is which direction, x or y?
X.
So it's all going to be in the x. So the y direction is 0 for the next one. How much of it is in the x? Well, 5 meters are in the x. Is it positive or negative? Positive, because it's to the right. Finally, the last part goes to the right and it goes up again. So they're both what? Positive, positive. Question is, we have all these positives that have no numbers. We have to figure out those numbers next to them then. Well, how do you find the horizontal component of something? It's the same rule for projectiles you've been using all the time. If you want to find VIX, what function do you use? Cosine. So take, ready? 7 cosine 22. I'm going to zoom in again here, actually. Give me a sec. You probably can't see this. Let me zoom in and do this better. So in this spot, put 7 cosine 22. How do you find the y component of a vector?
Sine cosine, or sine of 22 times 7.
That goes in the next box, up in the top right. And what do you think is going to happen here, guys? Yeah, except instead of 7 and 22, now you're using 4 and 15. Okay, so this is the horizontal component. And this is the vertical component. Now, all you need to do at this point to come up with the final, well not the final answer, but almost there, is add straight down in the x and add straight down in the y. This is what we were doing in our notes, but we didn't do it in a table. I said, add all the x coordinates, add all the y coordinates. And it wasn't as organized, right? So this is a little bit more organized, I think. So we have our last row at the bottom here, if we want, where we can add those values together. You can put a subtotal at the bottom. All that matters is these two. This does not matter. You're not going to put anything there. Okay, ignore that. That's what's important. So simply do on your calculator 7 cos 20 plus 5 plus 4 cos 15. So literally add straight down. Add all these numbers together. You can do it all in one line in your calculator. Make sure you close your parentheses after 22. 7 cos 22, close parentheses, plus 5, plus 4 cos 15, close parentheses, enter. What do you get for the overall x displacement, Honor?
I got 15.35.
Can somebody verify?
I got 15.5, but basically the same thing.
I got 15.
No, I got 15.4, which is just the rounded version of that.
I got the same thing.
So if you got 10, it means either you forgot The 5, did you add this 5?
Oh, no.
Yeah, that's probably why. But literally, guys, ready? Add this, and this. Now this column, what are you going to do? But the 10 needs to be negative. So 7 sine 22 minus 10 plus 4 sine 15. Plus 4 sine 15. So what does this mean? No?
I got that.
Wait.
I got that.
Check it in, okay? So, take a look. Ready? I'm going to go back to my diagram now. I'm going to go back to my diagram. Look at the diagram. Here's what this means. I'm going to give you the physical significance. 15.35. See this? Look what I'm circling, please. Look up. 15.35 is the distance from here all the way to here horizontally. Negative 6.34 is how far down they have to go. So really, this triangle should have probably, or these are not drawn to scale. This should have probably been a little bit lower. Maybe the 10 should have gone a little bit further down, the 5 here, and then the 4 ends up here. But the idea is that from beginning to end, you would have to go 15.35 meters over and negative 6.34 meters down. These are what you're getting, these values. Your goal is to figure out the resultant vector of this whole thing.
Oh, and you can just use
Pythagorean. Yep, that's it. Okay, use Pythagorean theorem. So this is your base of the triangle. This is the height of the triangle. Since it's a positive, negative, I go positive, then I go negative. So these sums are giving you the legs of the right triangle. Also, you need R, which also need this angle right here, theta. Okay? Yes?
Do we use like Y to say like the northeast?
Yeah, because think about this one, right? You're going east, and then you're going south, right? This is telling me positive in the X, which means go east, negative in the Y, which means go south. So it's going to be southeast at the end. You do. So at the end, once we get our numbers, we'll write that. I'll show you what I'm saying here. So the answer is going to be some number at some angle southeast. Okay, some degree measure and some meter measurement. So figure out what R is, figure out what the angle is, and it's at some degree southeast. Remember that vertical and horizontal vectors are only in the X and Y. That's kind of the tricky part here. Okay, when it says that the person moves 10 meters south, that's why we put a negative 10 in the Y direction only. You have a squinty look like you're confused. You want to ask?
No, I'm just trying to see the numbers.
Oh, in the diagram?
No, it's fun. I'm getting glasses today.
His eyes are
It's happening today.
You could also move up if you need to. So what do we get from Pythagorean theorem for the resultant vector LE? 16.6. Others agree?
Yeah.
Sounds about right. How do I know LE's on the right track? Because it's got to be bigger than these numbers. The hypotenuse has to be the longest leg. So if you got something less than 15.35, you clearly didn't do it right. Okay? How about the angle theta? Remember again, tangent. You've got opposite, you've got adjacent. What do you got, Ellie? Not Ellie, Zoe.
22.46.
Agreed? Okay? So 16.6 meters at an angle of 22.5 degrees, rounding, southeast. Yeah.
Do you have to use tangent to find the angle, or can you use...
Technically, no, because you can use the hypotenuse, because you know it. So you could use others. But honestly, start using it, because tangent inverse of y over x, right? Isn't this y? Isn't this x? Shows up all over the place in engineering, in physics, in calculus. So get used to using tangent inverse. It happens a lot. Okay? Tangent also gives you the slope of a line on a graph. So that's a very useful thing to figure out if you want the inclination of a graph on the line. Okay? Now, I would like to go to projectile motion at this point. The other class, I did a different example from vectors. So what should you probably do tonight?
Look at their video.
Yeah, check their video out tonight when you're practicing, in addition to maybe all the videos I sent you links to. Okay, those are resources for you to use. I'm also going to use different examples now for projectile motion. So hopefully they will be watching this video. Hopefully they're watching right now and listening. Get it? Because if they're listening tonight, they'll hear me talking as if it's now.
Oh.
It's kind of freaky, right? The future? Are you listening right now? See? It's kind of weird. They're listening right now. Anyway, so hopefully you guys watch the other videos, okay?
I was just saying hi to Thomas.
Oh, Thomas. Benno says hi. Out today, so he's going to be watching videos. So say hi to Frankie.
Hi, Frankie.
All right, so this is in the future. He's watching this right now. This happened a while ago. Kind of crazy, right, to think about that? By the way, any big Back to the Future fans? Everybody see all the memes lately? Because it's finally 2015, and it's finally like all this stuff that's happening.
And
Supposed to show up today.
This is supposed to show up today. Is it today, really?
Yeah, it's today.
Nice. I didn't know it was today. That's awesome. And the Cubs are supposed to win the World Series this year, too.
Nope.
Clearly, that's not happening.
So funny.
I love it. All right. So projectile motion. We have two types of problems. Horizontally fired and at an angle. The only difference is that horizontally fired, the velocity is in the x direction only. So let's go over both of those examples and how we'd approach these problems. So let's say that an object is launched from the height of 20 meters. And it's launched horizontally with an initial velocity of 5 meters per second. And we want to figure out the trajectory. I should use actually range since we started using the word range from our lab. I want to figure out the range. So how would I word a problem like this in the test? Here's what I would probably write. I would say the following. Benno is standing on the edge of a cliff. And he decides to kick a soccer ball over the edge of the cliff. He kicks the soccer ball with a horizontal velocity of 5 meters per second. The cliff's height is 20 meters. Determine the range of the projectile and the time it takes for it to land. I might ask you in part A to find the range and in part B to find the time. Or maybe I'll say find the time in part A and the range in part B. But usually I give you an order on purpose, right? So part A will probably help you with part B. So in this problem, it would be useful to find the time first. So part A will say find the time it takes for this object to land. Part B might say find the range of the projectile, which is what x is. That's what we're looking for here, which is x. It's very difficult to see that, sorry. We're looking for that x right there. Okay, so, and we're also looking for time. How do I approach this? How do I approach this? What do I start with for all these problems? How do I start them? Good. Make your table, your XY table to start, please. Not the vector table we did a moment ago. Different table, right? Tables are useful. They organize data very easily for you. So, what's the height of the cliff?
20 meters.
So what's the vertical displacement?
20. Wait, 0. Wait, no. Oh, wait, no. I just abandoned.
It's all right. You're close.
Negative 20.
Negative 20. Why is it negative, the vertical displacement? Because you're going
Down.
down. Whenever a problem is struck horizontally from like a ledge, the y is always going to be negative, right? Because it's always going to fall down. How about the x component? Unknown. What else? What else do we know? What was the velocity with which Benno kicked the ball? 5. So where does that show up, Nat? Horizontal.
Oh, because he's kicking it straight.
Okay, there's no angle involved here, so we don't have to do like, 5 times the cosine of theta and 5 times the sine of theta to get those values. What is VIY?
0.
It's always 0 when it's launched horizontally, and use common sense. Something launched horizontally means it's not launched vertically. If it's not launched vertically, it has no initial velocity in the y direction. The acceleration in the x direction is always,
0.
and in the y direction, this is all Natalie. Come on, others. Negative 9.81, good. So we've got the info that we can use. It's all listed. The question becomes now, and I can move everything up because I don't need it anymore. The question now becomes, how do I find time? Well, time is on both sides, right? How many missing variables do I have in the x direction? How many missing variables, Ellie? 2. So I can't do anything there yet. I can write my equation, but I really can't solve individually. If I have 2 missing on both sides, then I would need to use like a system of equations and substitution. But the y direction looks pretty nice, doesn't it? Look at the y direction. Looks like you're only missing time, just one variable. So, I know nothing about the final velocity, which automatically eliminates 2 formulas. Now, side note, write this down, side note. You're only going to ever use the final velocity in these problems when you're trying to find out something about max height. VF in the y direction, VFY, will only be used when you're trying to determine something about max height. And that's when objects are launched at angles. So in these problems, when it's launched horizontally, you're always going to use the same formula in the y direction. Who could tell me what that formula is that we're going to use?
Y equals then t plus 1/2 at squared.
You're always going to use that formula for these problems because we're not going to ever know information about VF. If I ask you to find the time it takes to get up to max height, you could set VF equal to 0 in the y direction, because at the top, what happens? It stops vertically. It's still moving horizontally, remember? Follow my pen, please. It's moving, it's moving, it's moving, it's moving, it's moving, it's moving. It's only moving horizontally, because vertically it stopped going up, and then it starts to come down, right? For an object to start coming down after going up, it has to stop, but it's only stopped in the vertical direction. The horizontal velocity is always the same. Why is the horizontal velocity always constant? Because acceleration is 0 in the x direction. So the horizontal velocity is always, always, always going to be the same.
But to find time, couldn't you do like v bar equals x over t?
But what are you missing?
Set out.
You're missing x and t. You're right, absolutely, Alejandro. And you're going to do that in another problem. The problems with the angles, there's a good chance you're going to end up using this, right? But you're missing x, so you can't get t there. So get t over here, move that over, and then we can get x. The goal was to find x, really, the range of the projectile. Okay, so let's get t. This drops off. Why do I do that? Because there's no vertical initial velocity, okay? It's 0, drops off, which makes that equation very simple. Your textbook uses y equals 1/2 gt squared a lot, which is what this is. When you drop this off, this whole thing is gone. That's pretty much 1/2 at squared, or gt squared. A and g are the same thing, gravity. What am I solving for? Time, right?
Yeah.
I'll plug in the numbers right now just to be a little simpler today. But if you are good at it and you want to solve algebraically, here you would have multiplied by 2 to get rid of the 1/2, divided by acceleration, and then taken the square root. Which is the same thing we're going to do here. Multiply by 2, divide by negative 9.81, and then take the square root.
And if we do it algebraically, can we just pop it in our calculator?
Absolutely. If you did this, ready? I'll show you. If you did the solution algebraically, it would be t equals 2y over a under the square root, and then just give me a number. I don't need to see the substitutions. No? Okay? If your givens are all right, and your generic solution is right, your number has to be right. I mean, unless you make a mistake in your calculator. I mean, I'll probably take off like a half a point or something if you do that, but you should not be making a mistake in the calculator at this point.
Do you care if we like only put the units at the end, or do you want it?
At the end is fine. At the end is fine. As long as they're right, Katie. If they're wrong at the end, then you're going to lose credit. If you do all the units right all problem, and then they're wrong at the end, I'll give you partial credit for the unit part. But you should know by now that if you're finding time, the units are seconds. Yeah. Connor.
Yeah, by 0.5.
No, you divide by 0.5. Yeah, you can divide by 0.5 and then divide by negative 9.81. But I prefer to multiply by the reciprocal. What's the reciprocal of 1/2? So multiply by 2, cancel this out, multiply by 2. Multiplying by 2 is the same thing as dividing by 0.5. Okay? What do you get for the time? 2.02? Seconds. I take that, I go over here, I plug in my VI as 5, I plug in a 2.02, and now I can figure out the range in the problem. Remember, linking variable. Here's your linking variable. It goes from the y direction to the x. It goes from the y direction over to the x. What do you end up getting for x when you multiply 5 times 2.02, Alejandro? 10.1. So that's how far from the base of the cliff this object would end up landing. Okay, this object would end up landing. How am I doing on time, guys?
4 minutes.
4 minutes? Okay. Let's do another problem. And what's that?
Shouldn't it be something different? Shouldn't it, like, isn't x equal velocity times time? So would it be like 20 times? Oh no, that's the velocity is 5. I think it was 20 for some reason.
Okay, because the lab we just did.
Oh.
The lab, the velocity was 20, remember? That's fine. Don't worry about it, it's just notes.
Yeah.
All right, setup of it, and then maybe you could finish it tonight on your own if you want to practice. So let's say that an object is launched at an angle of 25 degrees with an initial velocity of 30 meters per second. So right away, that's what I would draw to start this problem. An object is launched at an angle of 25 degrees with a velocity of 30 meters per second. I'd start just like that. And the problem says, determine if, in the other class I did determine if we'll make it over a wall. So if you want to look at an example of that, look at their video. I'll do determine the range. Determine the range of the projectile. Range means what again? Yes, very good. So this question, if I say find the range, I'm saying it's going to follow this path, and I want to know, what is this? Now, there's a trick to doing a problem like this, or something you have to recognize. Looks like you're not given enough information in a problem like this, but you actually are. You need to know the time. You can find VIX, you have x, or you're going to look for x, you need to know the time in the y direction. You know something about the y direction, whether you realize it or not. You know the acceleration, but what else? It starts on the ground, it ends on the ground. What's the displacement? 0. So why would he, even though the max height is some number, we're thinking of this as initial and this as the end of the problem. We're not looking for the max height right now. So what we get as a result here for our table is the following. We can list the following. VIX equals VI cosine theta. VIY equals VI sine theta. Acceleration in the y is gravity. The displacement in the y is 0 meters because it starts on the ground and it ends on the ground. It definitely travels up, so there's some vertical displacement halfway through, but at the end, it's still at the ground. Acceleration in the x is 0 as always. I'm adding units to the velocity, sorry. Meters per second, I should say. The x is what we're looking for. And to get x in the x direction, if we're looking for it, we need to know what time is still.
Wait, why would y be 0?
The velocity is not 0. So remember, it's launched at an angle like this. So the launch angle shows that it's launched vertically and it's launched horizontally. So there's velocity in both. But because it ends back on the ground, the vertical displacement from beginning to end is 0. Okay? It'd be like throwing an object up and landing back on the ground. It's the same thing, really. So here, what we'd have to do is the following. Zero equals whatever you get as a number here times time. That's VIY from up here, right? Take that number, plug it in right there, plus 1/2 negative 9.81 t squared. To get time, though, you'd probably have to factor out a t or use the quadratic formula where there's no c value there. Once you get the time here, that it takes. Plug the time in here. You have the velocity. You can find out what x is. Keep practicing. Practice, 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 practice. If you didn't get me the problem set, when you do submit it, I want an email when you submit the problem set if you haven't done it yet. If it's a hard copy, I want to get it by the end of the day, please.